Welcome back. We're continuing section 5.1, talking about extreme values, which again are maximums and minimums. And we're going to continue talking about critical points and how those can help us find extreme values. First off, a little bit of a review. Be a good idea to pause the video here and see if you can fill in those blanks. All right, critical points occur in one of two places, either where the derivative is equal to 0 or where the derivative is undefined. Maximums and minimums, otherwise known as extrema, always occur at critical points or possibly at the endpoints. You could put extrema right here. I'm going to put maximums and minimums just because that's what most students are used to. Question: extreme values always occur at critical points. However, critical points do not have to be extreme values. Can you provide an example of a graph that has a critical point but is not an extreme value? Again, it'd be a good idea to put the video on pause, see if you can come up with your own example. All right, there's several examples. Extreme values are where the derivative is either 0 or undefined. Derivative of 0 means it's got a slope that is horizontal. I could definitely have a slope that's horizontal, but not have a maximum or minimum, like right there. Or a critical point happens where the derivative is undefined. I could create several ways of being undefined and not have a maximum or minimum. One way is I could have a discontinuity, right? Derivative is undefined at discontinuities. Right there, I've got a discontinuity, but there's not a maximum or minimum there. If you wanted another example, right here, the derivative is undefined again because you can't be defined because the derivative is undefined at a corner. Yet that is not a maximum or nor a minimum either. Okay, so today we're going to continue yesterday's work, same type of thing. We're just throwing a few more complicated problems at you. For example, piecewise functions. We're going to find the critical points of that piecewise function, and we're going to identify any maximums or minimums that happen. Basically, it's going to be the exact same thing, except you notice where the function changes value right at 1. That's almost certainly going to be a critical point as well, right? Because when those functions come together at that point, in order for it to not be a critical point, it would have to meet at the same point and at the same slope, right? So that you have the same slope from the left and the right, and then the derivative would exist. There's lots of ways to find out if that is the case. One of the easiest ways is actually just having the ability to sketch something like this, which is definitely something we did in pre-calc. As a reminder, 5 minus x squared should be something we know how to sketch. It's going to be a parabola that's upside down because of -2, and raised up 5 because of that 5. You could also just put in different values, right? Like if I put in a 0 into here, 5 minus 2 times 0 squared is going to be 5. If I put a -1 in there, I can plot different points and get an accurate representation of the graph. That's what I'm going to do right now. All right, so I plugged in a bunch of different points. I knew it was an upside down parabola, so I started sketching it. I stopped right there when x was 1 because that's exactly where I'm going to shift to the next function. I stopped at a closed circle because x is less than or equal to 1, so it actually hits that point. If this was just a less than sign, I probably would have put an open circle there for now. And maybe that open circle would have gotten filled in by the other one, maybe not. Now I'm going to do x plus 2. I'm going to do the same thing. I'm going to plug in a 1, plug in a 2, plug in a 3, continue that one. All right, there it is. We should not be surprised that that is a linear equation. It's a line because that's a graph of a line with an y-intercept of 2. You'll notice, of course, I didn't go all the way back to a y-intercept of 2 because this equation starts at 1. Normally, if it had started like somewhere down here, I would have put an open circle because of that. But since it actually landed in the exact same place the other one left off, it just kind of filled in right where the other one left off. All right, being able to sketch that made it really nice because I can just look at that point now and say for sure there is a critical point at x equals 1 because that is clearly a corner, right? I could have done this analytically by finding the slope of this one and the slope of that one at 1. And I would have clearly seen that the slopes were different. So I didn't need to graph it, but graphing it can be really nice. So the derivative would be equal to a -4x whenever x is less than or equal to 1. And it'd be equal to 1 whenever x is greater than 1. If you plugged in a value of 1 into this one, I get a -4. I get a 1 out of there. Clearly -4 and 1 are not the same slopes, so I'm going to hit a corner. So I didn't even need to graph this to see the corner, but being able to graph it can make it really clear and make it really easy. All right, so I wanted to identify the critical points. So far, I know for sure I've got a critical point at x equals 1 because there's a corner right there. Then the other critical points that could happen is whenever the derivative is equal to 0 or when it's undefined. Well, if I look up there at that -4x, that can be equal to 0 whenever x is 0, right? I could set it equal to 0. -4x equal to 0. That only happens when x is equal to 0. Divide both sides by -4, right? So there's a critical point. And that's it, because this bottom part, that's never going to be 0, right? There's no x I can have that's going to make 1 equal to 0. So I've got 2 critical points. Again, at this point, we're just going to use a graph to be able to tell if those critical points are maximums or minimums. I can look here and say, oh, yep, that critical point at 0 is definitely a maximum. And that critical point at 1, that's definitely a minimum. Depending on your question, they may ask you to identify which critical points are not stationary points. Stationary points are, again, where the derivative is equal to 0. If the derivative is undefined, then it's not a stationary point. So those are both critical points. Out of those, only one of them happens to be a stationary point. It is this one, because that's where the derivative is equal to 0. So that's a stationary point. That one's not a stationary point. There we go. All right, let's try one more. Identify the critical points and determine the local extreme values. Identify which critical points are not stationary points. Same type of question. All right, this one, I don't expect you to be able to graph that one like we were able to graph this one, but we can still find our critical points. And then again, at this point in time, go ahead, use your calculator to graph it, but don't graph it first, because I'm afraid if you graph it first, you're gonna be like, oh, there's the critical points and maximums and minimums. We should really get used to being able to finding our critical points without a calculator. So critical points are where the derivative is undefined or equal to 0. So first step is to find the derivative. This is going to require the product rule, right? One and another one. Most of you guys at this point are probably rewriting this either in your head or out loud, or on your paper, because you're recognizing this would be a lot easier to do calculus with if I rewrote it with an exponent. All right, y prime. First times the derivative of the second. First is x squared times the derivative of the second. The 1/2 is going to come down, times 3 minus x, all to the -1/2 now, subtracting 1. Don't forget your chain rule. Multiply by the derivative of the inside. The derivative of inside is -1, so multiply by -1. Plus, finish off the product rule. I just did first times the derivative of the second, plus second times the derivative of the first. Second is 3 minus x to the 1/2. Derivative of the first is just 2x. All right, you can leave your answer like that. However, once we start talking about algebra and where this is equal to 0 or undefined, it tends to be easier to rewrite it in that square root form or take care of these negative exponents. So let's simplify this thing a little bit. All right, that's going to be a -x squared over 2 square roots of 3 minus x plus 2x times the square root of 3 minus x. All right, just a reminder where that came from. Since that's a 1/2 with a 2 in the denominator, there's a 2 in the denominator. That x squared times -1, that's where I got the -x squared. And a -1/2 power would be the square root, but in the denominator. That's where this came from. Some people like to find a common denominator and combine these together in one. Some people like to leave it. Let's go ahead and find a common denominator and combine these together because it might make it nicer. Common denominator would be 2 times the square root of 3 minus x. So I got to multiply 2 times the square root of 3 minus x here. So now I've got a common denominator. So now I've got a common denominator of 2 square roots of 3 minus x. I've got a negative x squared on the top, plus if I multiply these together, that would be, let's see, a 2 times a 2x, that's a 4x. And a square root of 3 minus x times a square root of 3 minus x, that's a 3 minus x, right? Because the square roots are going to be to the 1. Oops, I got rid of something. So that'd be 3 minus x. We can make this look even nicer. That'll be a negative x squared plus 12x minus 4x squared all over 2 square root of 3 minus x. We are moving past our page here, which would be a negative 5x squared plus 12x over 2 times the square root of 3 minus x. All right, I'm going to rewrite this up here so we got some room. Okay, that took a while, but there's our derivative. Again, I wanted to identify critical points. Critical points are either where the derivative is 0 or undefined. I like it in this form here because it's really easy to see when it's 0 or when it's undefined. It's undefined whenever the denominator is equal to 0, because dividing by 0 causes a function to be undefined. And it's equal to 0 whenever the numerator is equal to 0. Excuse me. So f prime is undefined whenever the denominator is equal to 0. So whenever 2 times the square root of 3 minus x is equal to 0, we could divide by 2, square both sides, and we could get x by itself, but hopefully it's pretty quick and easy to see here that the only thing that's going to cause that equal to 0 is when x is equal to 3. So there's one of my critical points. All right, f prime would be equal to 0 whenever the numerator is 0. So whenever negative 5x squared plus 12x equals 0. We could factor an x out of there. That'd be x times negative 5x plus 12. And then it should be pretty easy to see that it's going to have, there's two things that could make this equal to 0. Either x is going to be equal to 0, or that's going to be equal to 0, which means negative 5x would equal to negative 12, which means x equals 12/5. All right, so we kind of got off my page here, but hopefully we followed what went along. Found the derivative, found whether the numerator was equal to 0, found where the denominator was equal to 0. That gave me where my derivative was either 0 or undefined. Those are all of my critical points. So I have a critical point at x equals 3, at x equals 0, and at x equals 12/5. Again, at this point, I would say, all right, those are the only places I could find my maximums and minimums. I would graph my original function then with a calculator. Again, we're going to learn how to do that without a calculator later. And we would just say, hey, are those maximums or are those minimums? I'll do that really quick. Okay, so here's our graph of our original function right there. You can see at 0, that was one of my critical points. I've got a minimum at 12/5. I guarantee that's at 12/5. There's my maximum. And at 3, I have a minimum. You'll also notice that 3 is an end point. That shouldn't come as a surprise to us, because if I plug in anything bigger than 3 into my original functions here over here, I'll be taking the square root of a negative, which is an imaginary number and typically is not included in our domain. So I do have an endpoint at 3. Turns out that the math actually worked out, giving me a critical point at that point as well. So that's both an endpoint and a critical point. All right, so that's our lesson for today. We're going to continue some work on section 5.1. Couple of notes. First off, please note that number 40 has a typo. That's why it's got that little asterisk there. The problem should read 3 minus x, not x equal to 3. So when you get to that typo, just understand it should be a 3 minus x. And then the last note, again, you may use your calculator on the shaded problems. For now, we're going to learn in the next couple of days how to do it without a calculator. See you later.